Good morning, everybody. Hope you had a lovely evening and welcome to the My Tutor Online School for today. Starting off this morning, as always, we have a GCSE chemistry session. Today's session is going to be on metals, alloys and nanoparticles, and it will be an hour long. We'll have 45 minutes, as we always do, for Aman, our tutor, to teach the lesson, and then 15 minutes at the end for any questions. Lots of you would probably know a lot about Aman by now, as she's been teaching these sessions so far. But if you don't, she studies medicine at King's College London and has done over 150 lessons with my tutor. Always remember that these sessions are recorded, so don't worry if you miss something. You'll be able to have the link to the session afterwards, as long as you are signed up to the My Tutor Online School. And yeah, if you have any questions, then send them through using the chat or the Q&A. I'm going to hand over to Aman now.
Thank you. It's lovely to see so many of you back as well. So as Frederica said, today we'll be covering metals, so specifically the properties of metals. Yesterday we went over metallic bonding, so today we'll look at the properties. Then we'll just look at alloys and see what happens to the properties of metals when we have an alloy, and then we'll look at nanoparticles, so the uses and limitations of nanoparticles before we do some exam questions. So many of you will remember this slide from yesterday where we looked at metallic bonding. So just a quick recap of metallic bonding, just to help us to understand the properties of metals. Let's just remember then that metals, when they bond together, so if we imagine this diagram over here is sodium, when they bond together, these are all different atoms of sodium, we get something called a giant metallic lattice. So remember, ionic bonding is between metals and non-metals. Covalent bonding is between non-metals, and metallic bonding is between metals. So we get this giant metallic lattice. Someone asked me yesterday, what's a lattice? So I said yesterday, it's this crisscross structure that you get, and that's exactly what our metal looks like here. And as we can see, we've got these positive ions known as cations. You can use either term in your exam questions, it doesn't really matter. And the reason they're positive ions is because, as I said, if this is sodium, if we look at our periodic table, sodium has an atomic number of 11. That means its electron shell configuration has 2 in the first shell, 8 in the second shell, and 1 in the third and outer shell. That means for sodium to have a full outer shell of electrons, it prefers to lose this 1 electron rather than gain 7. It's easier for it to lose that 1 electron there. So for it to lose that electron, it becomes a positive ion. So remember then, because it loses 1 electron, the number of protons will be more than the number of electrons. It will be that there are 11 protons because the atomic number is 11, but there will only be 10 electrons because we've lost 1. So that's why in metallic diagrams, these positive cations are in regular layers and they're positive, and we've got these delocalized electrons all the way around. And remember, delocalized means that they're free to move, and the number of electrons will always be a multiple of the number of ions. So remember, by that I mean that in sodium, we know that there's 1 outer electron, so that means there's 1 electron per positive ion. Someone is asking, if the outer shell has 4 electrons, would it prefer to lose 4 or gain 4? To answer that question, it depends on whether it's a metal or a non-metal. If it's a non-metal, it will tend to gain 4. If it's a metal, it will lose 4. So remember, metals like to lose electrons, whereas non-metals like to gain electrons. Usually though, with this type of question here, where you've got 4 electrons that could be, in the outer shell, it will be covalent bonding that occurs between 2 non-metals, in which case they would share electrons. But very good question, thank you. So as I mentioned, we've got these positive ions with this sea of delocalized electrons, and the really important thing is that we've got this strong electrostatic attraction between the positive ions and the sea of delocalized electrons. And as you might imagine, as the number of electrons increases, the electrostatic attraction increases. So by that, if we look at our periodic table, let's imagine we've got aluminium over here. We know aluminium, its electron shell configuration will be 2, 8, 3, and that's because it has an atomic number of 13. So 2 plus 8 is 10, plus 3 is 13. So it has 3 electrons in its outer shell, in which case it will lose 3 electrons to become an Al3+ ion. And that means in its diagram, instead of having 1 electron per positive ion, it will have 3 electrons per positive ion. And that means there are stronger electrostatic attractive forces between the positive ions and the electrons. Okay, so that's just a quick recap of what we covered yesterday. So now that we know about that structure, let's think about the properties of metals. So the first thing to understand is to be able to define all the terms that they use. So the first one is malleable. And malleable means that the metals can be hammered or they can be struck, and therefore they can form different shapes. And the key thing is, when we strike a metal or when we hammer a metal, it does not break. It will form a different shape, but it will not break. And we need to use the metallic structure to understand why that is. So if we go back to our diagram, so I've told you that malleable means that it can be hammered into different shapes without breaking. So why is that? Well, if we look at our diagram, we know that these regular layers of cations, because they've got these delocalized electrons in between the cations, these layers can move over one another. And so if we imagine, I'm just going to draw the metal diagram again, just a smaller version. So if we imagine this is, let's say this is magnesium, in which case there will be 2 electrons per cation, and that is because magnesium's atomic number over here is 12. So it's got an electron configuration of 282. So it will have 2 electrons per ion. Now let's say that I hit magnesium over here. So what will happen to that magnesium? Well, the particles are going to move. So it might become, or look a bit more like this. I strike it. So if I've put a hammer here, we might imagine that the particles move like this, but they haven't broken apart. And the reason for that is that the layers can slide over one another, but instead of these ions repelling each other, so remember, because they're positive ions, we would expect positive ions to repel because 2 positives do not attract. So we would expect these ions to repel, but because of these delocalized electrons in between, I'm not going to draw all of them, I'll just draw a couple. Because of these delocalized electrons in between, it holds that structure together. So the reason that metals are malleable is because these ions, these layers of positive ions can slide over one another and therefore change the shape of that metal without breaking it, because there are still strong electrostatic forces of attraction between the positive ions and the electrons. Someone is asking, will we be covering nanoparticles today? We will be. And someone else is asking, how do we find how many electrons to use per protons? That's a really good question. So when we're looking at our periodic table, we look at the atomic number. So for example, if we look at potassium, potassium has an atomic number of 19. That means there are 19 protons. And remember, the number of protons is equal to the number of electrons. So if the number of protons is equal to the number of electrons, that means there are 19 electrons. So we can do the electron shell diagram. The electron shell configuration says that 2 go in the first shell, 8 go in the second shell, and these are just rules to learn. The third shell can also have 8. 8 plus 8 is 16, plus 2 is 18. That means in its fourth and outer shell, it has 1 electron. So for potassium, each positive ion would have 1 negative electron. And that also means that the number of protons then would be 19, but because we lose 1 electron in potassium, it would be 18 for the number of electrons. And remember, to find the number of neutrons, we look at the mass number, which is 39, and we do 39 minus the number of protons, which is 19, to then get the number of neutrons, which would be 20. Okay. Can I draw potassium? I can. So the metallic diagram of potassium, again, it doesn't matter how many cations you draw. What's really important is that you have the right number of electrons. So someone's asking me to repeat that, so I will repeat that for you. So if we look at potassium, it's got an atomic number of 19. That means there are 19 protons. Remember, in atoms, the number of protons is equal to the number of electrons, and that is because atoms are not charged. So if 19 is the number of protons, that means there are 19 electrons. So to do the electron configuration, the first shell would have 2, the second shell would have 8. Again, these are rules that you just have to learn, that the first shell has 2, the second shell has 8, the third shell has 8. 2 plus 8 is 10, plus 8 is 18, but the atomic number is 19, so that means the fourth and outer shell has 1 electron. And what that means then is it's easy for that potassium to lose that electron to get its full outer shell of electrons to get that noble gas structure. So it becomes 288, and it will have a positive charge, and that's because it loses that 1 electron here. So that means the number of protons will stay at 19 because 19 is the atomic number, which is the number of protons. But because we've lost an electron, the potassium becomes charged, so the number of electrons is 18. So to draw that as a metal, again, as I said, it doesn't matter how many cations you draw, it's about the number of electrons being right for the number of cations. So if I literally just drew, if I drew 6 ions, that means I would need 6 electrons because the number of electrons is 1 per cation, like that. So that could be our potassium metals all joined up. So remember, these are all different potassium ions. Okay, so back to our metals then. So we said that they're malleable, they can be hammered into different shapes without breaking, and we said that that's because the layers can slide over one another. Well, it's exactly the same for ductility or ductile. So ductile means that metals can be drawn out into wires. And just like with malleable, because the layers can slide over one another, so because these layers of cations here can slide over one another without breaking that shape, they're also ductile. Someone's asking, can metals or can these ions be negative? Metals will never be negative, they're always positive, because with metals they always have quite a few number of electrons in their outer shell, so it's easier for them to lose electrons than to gain electrons. So metals prefer to lose electrons and therefore become positive. Non-metals prefer to gain electrons and become negative. Okay. So we've explained malleable and ductile. Remember, it's about the layers moving over each other, but that structure not breaking because of the fact of those delocalized electrons providing that electrostatic attractive forces between the cations and the electrons, meaning that those positive ions do not repel. The next thing is high melting and boiling points. That's quite a nice one to explain, and that's just to do with the electrostatic attractive forces between the cations and the delocalized electrons. So they are very, very strong, which means that metals have high melting and boiling points. So it's all to do with the forces. You'll remember with all the bonding we've covered, the melting and boiling points is always to do with the forces between the particles. So you'll remember in ionic bonding, it's the forces between the positive and negative ions. In covalent bonding, they have low melting and boiling points because there are intermolecular forces between molecules. And so we don't break covalent bonds. And then in metals, we have this high melting and boiling point because of the electrostatic attractive forces. So someone is asking me to re-explain ductile, of course. So ductile means that metals can be drawn out into wires. And the reason for that is the same reason as malleable. It's because these metal ion layers, so if we go back to the structure, these layers of cations can slide over one another. So if we draw a metal out into a wire, we're effectively changing the shape of that metal. Just like malleable, that structure is not going to break when we draw it out into a wire, and that's because those layers can slide over one another, but those ions won't repel. We would expect positive ions to repel, and they're not repelling because of these delocalized electrons. Someone's asking, are nanoparticles expected to be known for foundation tier? No, they are not. What does drawn out into wires mean? So if you imagine a coil or a coil of wire, so for example, a spring, that is like a wire of metal. So a spring, that's a wire of metal. So instead of it being a big clump of metal, so let's just imagine this is a big solid block of iron there, it can be drawn out into a spring type wire like that. So that's what ductile means. Whereas malleable just means that if we hit the metal, we can change the shape from something like this to say something like this. So I hope that makes sense with ductility. And again, it's all about those layers sliding over each other because of the delocalized electrons there. Okay, someone's asking, why does it have a high melting and boiling point? And that is simply because of those electrostatic attractive forces between the cations and the electrons. They're really important and they're very strong, and so that means that we have to apply a lot of heat to melt or boil a metal. Someone is asking, does this mean products such as jewelry are alloys instead of pure metals, please? You are exactly correct. So the one problem with metals is because these ions can slide over one another, that means that metals or pure metals tend to be very soft. So a lot of jewelry is made from alloys such as stainless steel. You can get sterling silver, but sterling silver tends to be a coating over already what's there that could be an alloy. So someone is also asking me, do we need to know all these properties? We do need to know most of these properties for the foundation tier, and for the higher tier, you definitely need to know all of these properties. It is across all the exam boards that you need to know all those properties. Someone saying, so a cheaper metal may be stronger. Exactly, and we're going to come on to alloys in just a second. And are they good conductors because of the delocalized electrons? That's really excellent. So the final property of metals that we're going to cover is the fact that they are really good conductors of thermal and electrical energy. And you'll remember that metals have these delocalized electrons, so these little blue electrons here that I've drawn. And because of those delocalized electrons, they can carry a charge through that metal structure. And it's really important when you're answering exam questions, you say that they can carry a charge. So if we now know that they're malleable, they're ductile, they have high melting and boiling points, and they can carry out a charge, that's all you need to know about metals, just remembering that they're also quite soft. So let's move on to alloys. Okay. So this is the definition here of an alloy, a mixture of two or more elements, of which at least one is a metal. So some of the examples of alloys are steel, brass, and bronze. You wouldn't be expected to know what makes up steel, brass, or bronze, or any of the other alloys. You're just expected to know that they are alloys. And the reason we know they're alloys is because you won't find those on the periodic table. They will always be made of at least one metal, and usually another element that could be another metal, or it could be a non-metal. So the first and key thing that all exam questions tend to ask is, why are alloys harder than metals? So to answer that, let's draw the structure of an alloy then. So let's say that we are drawing steel, which is iron and carbon. So if we draw, let's just say these are our iron ions, so that's probably a bit confusing, but these are our positive ions. And then let's just say we've got a particle of carbon in there, and then we've got more ions, and then another particle of carbon, and another ion. Okay, so let's just say that is our steel. And as I said, you don't need to know what makes up steel, but what we do need to know is that it always has one metal in it. So steel, though, I will tell you, is made of iron and carbon. So these blue particles here, let's imagine they're carbon, and these pink ions are iron. Okay, so first thing then, why are alloys harder than metals? Well, let's have a look. They've not got these regular layers, so we can't slide these layers over one another. And the reason for that is because of these smaller particles disrupting those layers. So often exam questions are looking for the fact that alloys disrupt the layers. So someone is asking me, can alloys be compounds? It's a really good question. They are not, they're mixtures. They can be compounds in certain scenarios, but in an exam question, if it asks you what is an alloy, you always say a mixture. And the reason for that is because of the difference between physical and chemical bonding. So to explain that, I'm going to do that very briefly because it's not part of the syllabus and you don't need to know why, but just as a brief explanation. In this diagram here, all the iron ions are bonded together electrostatically. They've lost electrons. Whereas these carbon atoms, they have no bonding with the iron. They are physically bonded. And by physical bonding means that there's very weak forces between the iron and the carbon. But there are strong forces between the ion. We know there are electrostatic forces. Those electrostatic forces are chemical bonding. Ionic bonding, covalent bonding, metallic bonding is all chemical bonding. So remember, the definition of a compound is that you need to have two or more elements chemically combined. In an alloy, the other particle, so the non-metal, tends not to be chemically combined. It tends to be physically combined. So it tends to just be there. It is part of that structure, but it's not chemically combined. And that is why alloys tend to be mixtures. They can be compounds if you've got two metals in there. If you've got two metals in there, often they will be compounds. But for the purposes of exam questions, if they ask you, the answer is always a mixture. I'm a bit confused. If something is more malleable, wouldn't that make it harder? Not really. So if something is malleable, that means the layers can slide over one another. And because the layers can slide over one another, that means a metal can easily be shaped. So that makes it soft. Okay. Can you re-explain why it's harder? Of course I can. And sorry, just before I do that, someone is asking, will alloys be ionically bonded? No. So I've just explained that alloys tend to have this physical bonding. There doesn't tend to be ionic bonding in alloys. So there doesn't tend to be chemical bonding. So chemical bonds are ionic bonds, metallic bonds, covalent bonds. Physical bonding, it tends to be kind of almost like intermolecular forces. They tend to be almost like that. So there's this very slight forces between metals and the non-metal So they are mixtures. There's no ionic bonding in alloys. Do we need to know about physical bonds in our exams? We don't. Okay, so just to explain why an alloy is harder. So these ions here, these positive ions, in a normal metal can slide over one another. Just like here, we've got this regular structure, these nice layers. That means these positive ions can slide over one another like this. And that means that the reason that happens is because these ions won't repel. The electrons there will hold them together and allow them to move. Whereas in an alloy, we've got these smaller particles, sometimes they're larger, and that disrupts the layers. They're no longer in this regular arrangement, and that means that those layers can't slide over one another because we've got smaller particles here, so it's really hard for these layers to slide over one another, and that makes alloys harder, and that's why they are often used in things like cooking materials, in things like jewelry, because we don't want soft metals. Okay, so someone is asking, why do they have less electrical conductivity? We're about to come on to that. And someone is asking, what were the other bondings considered as chemical bonds? As I said, ionic, covalent, and metallic bond. Are different elements different sizes then? Yes, they are. So we covered this, I think last Friday, where we talked about how, actually on Monday, where we talked about there's a limitation of particle theory, where we assume that all particles are the same size, but they're not. So some metals will be much bigger depending on their mass, whereas something like carbon has a very low mass, so that's going to be smaller. So in this case, carbon would definitely be smaller than iron, so I've drawn carbon as smaller. And you can use your periodic table to help you there. So for example, carbon has a mass number of 12, whereas iron has a mass number of 56. So we know that iron must definitely be bigger than carbon. Do alloys have higher melting and boiling points? Now that is a really good question. It depends on what alloy it is. So if there are two metals in there, often they can have higher melting and boiling points, whereas actually most alloys will have a lower melting and boiling point. And the reason for that is because there's not that strong electrostatic attraction going on here, because we've got this disruption of carbon in there. So these strong electrostatic attractive forces are disrupted because of those carbon particles in there. So why are they less malleable and ductile? And that's the same reason for why alloys are harder. It's because those layers can't slide over one another that easily because of that disruption of the layers. So the key thing exams are looking for, are you saying that the non-metal particles or the other element in there will disrupt those layers, and therefore the layers cannot slide over one another. And that means that often alloys are less malleable and ductile. Note how it says less. They can still slide over one another, but it's just not as easy. There's a lot of resistance there. And that's the same thing for electrical conductivity. It's about resistance. So although these ions still have their delocalized electrons, often delocalized electrons can move through that structure, but because of these carbon particles here, there's that resistance because carbon doesn't have delocalized electrons, So there's resistance as it goes around the atoms of carbon, and that's why alloys tend to have less electrical conductivity. Okay, so just as a recap then, this is the structure of an alloy. You've got different elements in there and they disrupt those layers, meaning that it's harder for those cations or those positive ions to slide over one another, making alloys hard, making them have less malleability and ductility, and making them less electrically conductive because the electrons, these delocalized electrons, face resistance. Okay, so we're moving on from alloys now onto nanoparticles. So we covered nanotubes yesterday, which is here, these carbon nanotubes that we covered. This is just a random picture. I'm not going to be going through all of those. Just a picture of some different types of nanoparticles that you may have. The ones that we need to know about with regards to metals and what this covers, we'll be looking at in the next slide. But for now, let's try and define nanoparticles. So everyone yesterday told me that nano means very small. You're exactly correct. It does mean very small. Precisely, it's 1 × 10 to the -9. And all nanoparticles will tend to have between 1 to 100 nanometers diameter. So often you can use that as an answer as well. So nanoparticles will be between 1 and 100 nanometers in diameter. The key thing I want to look at today is this large surface area to volume ratio, because this is the main thing for why we use nanoparticles or why they're so important. So yesterday we briefly covered this, but we'll look at it in a bit more detail today. So I want you to imagine a really big cube. So let me draw a bigger cube. So let's just imagine this is our really big cube and it is 10 centimeters by 10 centimeters. Okay, so to do the volume to surface area ratio, surface area to volume ratio, we need to work out the surface area and the volume of our cube. So if you do maths, you'll remember to calculate the volume of a cube. We do 10 times 10, so the surface area of one surface times the depth. So 10 times 10 times 10 is 1,000. So that means the volume of this cube is 1,000 centimeters cubed. The surface area, to calculate that, we calculate the area of one surface and then we times it by the number of surfaces. So the area of one surface is 100. The number of surfaces in a cube is 6. So if we imagine there's one here, one on the back, one here, that makes 4. 1 on the top and 1 on the bottom. So there are 6 surfaces on a cube. So that means the surface area is therefore 600. So 10 times 10 is 100 is one surface, and we times by 6, which makes 600. Okay, so someone is asking how many nanometers make up a centimeter. We will be covering that in just a second. So 10 times 10 is a 100, and we times that by 6 to get 600 centimeters squared. Okay, so there are 1,000 centimeters cubed and 600 centimeters squared. So the ratio of surface area to volume is 600 to 1,000. Okay, so if we now try and make that to 1, because obviously like this, we don't really understand the ratio. So if we want to make it something to 1, to make this side 1, we divide by 1,000. So 1,000 divided by 1,000 is 1. That means if we do that to that side, we need to do the same to the other side. So 600 divided by 1,000 is 0.6. So the ratio therefore reads 0.6 to 1. So now if we take a smaller particle, because remember nanoparticles are smaller, so if we take a smaller cube, and let's just say it's 1 centimeter cube here. The volume of this cube would be 1 times 1 times 1, which is 1 centimeter cubed. And the area, or the surface area of this cube, would be the area of one surface times 6. So the area of one surface is 1 times 6 is 6, which gives us 6 centimeters squared. So the surface area to volume ratio here is 6 to 1. If we compare that with the larger cube, that was 0.6 to 1. So that means a smaller cube or a smaller particle has a larger surface area to volume ratio. But what does that mean in terms of nanoparticles? Well, it means that there are more particles on the surface. So because it has a larger surface area, that means there are more particles on the surface, or more atoms on the surface of a nanoparticle. And what does that mean? It means that they're highly reactive. Because if there are more atoms on the surface of our nanoparticle, it means that more can react. And that is why they are often used in things like catalysts, because if they're, you remember, catalysts speed up a reaction. So if you've got more atoms there to react, they can be used as catalysts. And the other thing is that smaller quantities are needed. So and the reason for that is because we've got so many particles on that surface, we don't need as big of a quantity as, say, something like a bigger particle, so a normal particle. So someone asked me how many nanometers in a centimeter. 1 times 10 to the power 9 is the difference between them. So you use that to work out how many, that's the difference between the centimeters and nanometers. Someone is asking, because mercury is a liquid at room temperature, why does it differ from other metals? So that's a really good question. So we're actually going to come on to different metals now and why they can be used as nanoparticles. A lot of metals have different properties, and that's why we have so many different metals. The key thing is you don't need to be able to explain why metals have properties. You need to be able to explain how you can use those properties. So for example, mercury being a liquid at room temperature basically means that it has a lower melting point than most metals. So we know most metals are solids at room temperature, but mercury is a liquid at room temperature, and that must mean it has a lower melting point. So that's just a property of that specific metal. Perhaps it has less electrostatic attractive forces between the cations and the electrons, or there's a different reason there. The important thing is we don't need to be able to explain why, we need to be able to explain how we can use it. So if we're looking at nanoparticles and the use of nanoparticles, again, the same thing remains. We need to be able to explain why we can, how we can use those nanoparticles. So someone's just asked me to go back to the nanoparticle slide, so I've just gone back to there quickly. Someone is saying, wouldn't 10 to the minus 9 correlate to the number of meters in nanometers instead of the numbers in centimeters? Yes, sorry, I said that the wrong way around. Okay, all right, so let's go then to the uses of nanoparticles. So I'm just going to cover 4 uses today. For the exam purposes, all the exam boards in the higher tier ask about nanoparticles. I've checked that for you, and you do need to know about a few of the uses. The one that comes up the most and is uniform amongst all the exam boards is titanium oxide. So we'll cover that as well. So let's start off with cosmetics such as sunscreen and face creams. So why do we use nanoparticles in that? So the first thing is the metal that's used is zinc, and zinc has a property that it reflects UV light. So that means it is used in sun creams because it's going to stop our bodies and our cells being exposed to that sun and therefore potentially dying. So that's why zinc is used to reflect UV light. So it stops us absorbing that UV light, which is really important. Now, zinc on its own is white. So if we use it in sun creams, it's going to make the sun cream white, whereas as a nanoparticle, because it's so small, it's invisible. So a lot of people prefer invisible sun creams. They don't leave that kind of white layer that you might see after you've tried to rub it into your skin. And so that's why often now sun creams are made of zinc oxide nanoparticles, because nanoparticles are really small. They actually reflect UV light a lot better, because remember I said there are more particles on the surface of nanoparticles because, there are more atoms on the surface of nanoparticles because they have that large surface area to volume ratio. So that means that they often reflect UV light a lot better than normal zinc or bulk zinc. And that's why we use nanoparticles in sun cream. So they're invisible, they reflect UV light better, and often we need less of them. Okay, the next example is self-cleaning windows. So titanium oxide, this is the one that I said is kind of the same across all exam boards. The reason we use titanium oxide is because titanium oxide has the property of being able to break down dirt. Whereas as a nanoparticle, it has the same property, but it does it a lot quicker because again, titanium oxide nanoparticles have more particles on that surface because they've got a larger surface area to volume ratio, which means they can break down that dirt a lot more quickly, and also less is needed. So if we look at this diagram here, this is our window with the titanium oxide nanoparticles on it. The sun will hit that window, and if there's any dirt on that window, the titanium oxide will break that dirt down, and then it rains and that gets washed away. So that is why it's a self-cleaning window. So the titanium oxide nanoparticles will break that dirt down and the rain will wash it away. And the reason we use nanoparticles is we need less of them. They are faster to react. Remember, they're catalysts, so they break down that dirt a lot more quickly as nanoparticles, and they're invisible. Okay, the third use is silver. So silver has the property of being an antibacterial. So often it's used in hospital equipment. It can also be used in socks. Someone's asking, are particles alive? No, they're not alive. Remember, for something to be alive, do you remember that it has to be able to move, it has to be able to respire, and you'll cover this in biology, but no, particles aren't alive. Someone's asking, if it has a higher surface area to volume ratio compared to bulk products, does this mean the properties are likely to be different? With regards to the properties, they're the same, although it tends to do things a lot faster, and it means that you need to have less of the nanoparticles. What is the difference between particles and atoms? There's not much difference. The main thing is a nanoparticle can have atoms in it. So remember, atoms are the smallest particle, if you want, in existence, whereas a nanoparticle could be a bigger particle. So zinc oxide nanoparticle is made of lots of zinc oxides, and zinc oxides are atoms. Or, well, actually zinc oxides are compound, but each nanoparticle has lots of atoms in it. So zinc would be an atom, oxygen would be an atom, but they're chemically combined to make a compound. So back to silver. Can nanoparticles cure cancer? We're going to come on to that fourth one in just a second. So silver nanoparticles have this antimicrobial property, which means that they're used in socks and hospital equipment. And again, we don't need to know why, we just need to know that we can use less silver, and as a nanoparticle, it's invisible, it's much smaller, so it's easier to use in hospital equipment. We will be doing an exam question in just a second, we're nearly finished. So finally then, with gold. So gold has the property of being used in a nano cage. So you remember yesterday we looked at nanotubes. Today we've got nano cages, and nanotubes are carbon, nano cages are metal, so gold here. And that means that what they can do is, because they're so small, they can get to tumour cells. Now the key thing about tumour cells is that they will have blood vessels in them, and tumour cell blood vessels tend to be leaky. By that, it means that they have little holes in them. Now the gold nanocages are so small they can get into those holes, but normal blood vessels don't have those holes, so gold will not get into normal blood vessels and affect our normal cells. When they get into that tumour cell via those leaky blood vessels and those holes, a laser can be directed at that tumour, and then what will happen is the gold will start to heat up, or that nanocage will start to heat up, and that will effectively kill that tumour cell without killing normal cells, because the gold will only be within the tumour cell. So that is one of the potential uses of nanoparticles. So we've covered all four that I think are important and are there across all the exam boards. The main one that you should know about is titanium oxide. So let's go on to an exam question. But before we do that, very, very quickly, we just look at some of the limitations of nanoparticles. So the first thing is they can be dangerous. Because they are so highly reactive, that means that they could potentially cause a dangerous reaction inside the body if they get to the wrong part, if they got to the wrong areas, or also outside the body. For example, if electricity or something hits a nanoparticle, because they're so highly reactive, they could be an explosive reaction. The other thing is, if there are nanoparticles in the air, so because nanoparticles are being used so much now, they could just be in the air. And if we breathe them in, they could damage our healthy lungs or damage other areas of the body, because we don't know how they would react with normal healthy tissue. And the final thing is that, for example, silver is used as an antibacterial, or silver nanoparticles are. And if they get into water, for example, from washing, they could potentially kill our fish or our aquatic life, because again, we don't know how they react with regards to other normal living beings. So that today we've covered metallic bonding, the properties of metals, alloys, and nanoparticles. So let's go on to some exam questions. So here we go. The picture shows a copper kettle being heated on a camping stove. This finishes at 10:45. Copper is a good material for making a kettle because it has a high melting point and it's a very good conductor of heat. Explain why copper, like many other metals, has a high melting point. So does anyone know, why does copper have a high melting point? You should describe the structure and bonding of a metal in your answer. Okay, so people are saying strong electrostatic forces because they can slide over each other. So it's not about sliding over each other with a high melting point. Remember, high melting and boiling points are always to do with the forces. So here, the answer would be that metals form giant metallic lattices and therefore have layers of positive cations or positive ions surrounded by delocalized electrons. A lot of energy is needed to break the strong electrostatic attractive forces between the electrons and the positive ions. That is why copper, like many other metals, has a high melting and boiling point. Okay, well done to everyone that answered with similar kind of answers to mine. All right, so this is a question on nanoparticles. So toxic socks. Silver nanoparticles are added to the fibers used to make some socks. Silver has a special property that it can kill bacteria. As a result, there are no unpleasant smells when wearing these socks. Some scientists are concerned about the use of silver particles in socks. The silver can be released from the socks when they are washed. This silver may end up in rivers. Silver in rivers may kill fish. Scientists found that some makes of socks release the silver more easily than others. Socks in which the silver nanoparticles are trapped in the fibers released very little silver when washed. So part A, suggest why silver stops unpleasant smells when wearing the socks. What do we think? Why does silver stop the unpleasant smells when wearing the socks? Okay, so yeah, it doesn't break down dirt, but it's basically an antibacterial. So they've said that there, it can kill bacteria, so it's an antibacterial. And it's really important that you say antibacterial here because in the question they've said it kills bacteria. How is the size of silver nanoparticles different from normal sized particles? Good, people are saying they're a lot smaller. Excellent, so they are very small. And you can say 10 to the -9, you can say 1 to 100 nanometers diameter. The silver nanoparticles are more effective at preventing unpleasant smells than normal sized silver particles. Why? Why are silver nanoparticles more effective at preventing smells than a larger size silver particles or normal size particles? Excellent, everyone's saying they have a larger surface area to volume ratio. Brilliant, so that means there are more particles on the surface and you would get the mark for just saying they have a larger surface area to volume ratio. It basically means they're more reactive, which is excellent. The final question then is the silver nanoparticles should be trapped in the sock fibers. Use the information in the article to explain why. So I'll go back to the article. It says the silver nanoparticles should be trapped in the sock fibers. So why should the silver nanoparticles be trapped in the sock fibers? What do we think? Why should we trap them? Brilliant, so someone's given me an excellent answer. They've said if they are trapped, they do not leave the sock when washed and hence they do not end up in rivers and cause harm to the marine ecosystems. That is a brilliant answer. Brilliant. Someone else is saying if they aren't trapped, then they won't be released when they're washed. Yep. Brilliant. So another reason you could give is if they're trapped there, not just about harming the marine life, but also if we put them in the washing machine or something like that, they won't leave the sock. Whereas if they're not trapped, as soon as we put them in the washing machine, the silver nanoparticles would wash away. So that would be another reason. Excellent. Okay. But yes, I prefer the answer of it reducing harm to the fish, which is I think also what they're looking for here. Someone's asking, are nanoparticles used up as they perform their function? So it's like a catalyst. So you remember with catalysts, they are partly used up, but usually they remain there. It depends what type of nanoparticle they are. Often silver nanoparticles are so small and they have so many atoms on their surface, they won't get used up because you have so many atoms there. It depends what nanoparticle it is. With regards to the body, when someone's asked me before, are the nano kind of tubes or the cages used up in the body and what happens to them? It depends what they're used for. So for example, with the gold nano cages where they go into tumor cells, and remember they go into the tumor cells because of those leaky blood vessels that have holes in them, whereas our normal blood vessels don't have holes. So they can get into tumor cells, these gold nano cages. And when they're there, we direct a laser at them. that heats up the gold nanocages and destroys the tumour. When we heat up that gold nanocage, it also destroys the gold nanocage. So that's how some nanocages are removed from the body. As I said, a lot of nanocages or nanoparticles aren't actually used in the body because we're aware that they can harm the body. So we only put them into the body if we are sure we can remove them from the body. So gold nanocages can be removed because when we heat them up, they're destroyed. Okay, so we'll do one more exam question and then we'll move on to the Q&A. So this is kind of a summary question because we've covered all the types of bonding now. So give one substance that has a very low boiling point. Which one do we think that is? Yep, good. So we've had some different answers. So we've got answers ranging from A, B, and C, and E. Okay, so let's go through what each of these are then. A is most likely a metal. That is most likely a metal structure there with our regular ions. So we know A has a high melting and boiling point. This is most likely to be diamond because the black blobs, there's only one type of black blob there, so that means it's probably carbon, and that's the structure of diamond. This is methane, CH4, and therefore it has covalent bonding between it because carbon and hydrogen are non-metals, and we know covalently bonded structures have low melting and boiling points, not because of the covalent bonds, but because of the intermolecular forces. So remember, methane does not go around as just one molecule of methane. There will be lots of molecules of methane, and you'll have those intermolecular forces between those molecules of methane. So these dots are my intermolecular forces, and they are very weak, so you only have a low boiling point there. Okay, which one's a compound? Brilliant. So a lot of people are saying D. D is the compound. So remember, a compound has to be formed from two elements chemically combined. C is also a compound. We'll go through that in just a second. So D is a compound. This is probably silicon dioxide, where black is the silicon and the white blobs are oxygen. So silicon and oxygen, two elements chemically combined, therefore D is a compound. And the other one that could be a compound is C, because C is made of carbon and hydrogen and they're chemically combined. Remember, covalent bonding is a chemical bond, so they are chemically combined. Which one's the metal? I've already annotated that on the screen. Yep, A. So A is the metal. We've got that regular giant metallic lattice structure there. They've not drawn in the electrons, but it's safe to assume that that is the metal. Okay, well done. So we'll just take some Q&A questions, and then if we've got time, we'll do another exam question.
Thanks, Aman. That was brilliant. Cool. Quite a few questions coming through. Some have said, what is the difference between silver nanoparticles and normal silver particles?
Excellent. So if you imagine silver as a metal, so silver as a normal particle will be a big clump of metal, whereas nanoparticles are so tiny we can't see them with the naked eye. So if we use silver nanoparticles, A, we can't see them, and B, they're a lot more reactive. So if we use them in things like hospital equipment as an antibacterial, we don't need to use much of them because they've got this large surface area to volume ratio, which means that there are a lot of atoms on the surface of that nanoparticle which can then react. We don't want these big clumps of silver on our hospital equipment. We'd much rather have these particles that are invisible to the naked eye, and also they have very little mass as well, which means that we can't feel them.
Great, thank you. Are nanoparticles used up as they perform their function?
Great. So I talked about this just a second ago. So remember I said that often nanoparticles are used as catalysts, and because they have so many atoms on their surface, it would take a long time for them to be used up, but it depends on what type of nanoparticle it is. So for example, I mentioned gold nanocages. When they are heated up in the body, they are used up. They're heated up, they're destroyed. Silver nanoparticles often last for a very long time, especially if they're trapped in the socks because they have so many particles on the surface. Again, titanium oxide lasts a very, very long time. And that is simply because there are so many atoms on that surface that it doesn't matter how many times the sun hits that window and destroys the dirt, it will continue doing it for ages. And that's why that's one of the main uses of nanoparticles, because they can last so long.
Thank you. Because mercury is liquid at room temperature, why does it differ from other metals?
So I covered this as well. I said that a lot of metals have different properties. The main difference between mercury and other metals is that it has a low melting point. So remember, most metals are solids at room temperature because they have those high melting points because of those electrostatic attractive forces between the cations and the electrons. Mercury has a low melting point. Again, you don't need to know why this is, but one of the reasons is because those electrostatic forces between the cations and the electrons are quite weak, and that makes mercury a liquid at room temperature. But just like many of these metals, a lot of them have different properties. That's why we have so many metals, and all of them have different kind of uses. As I said, you just need to be able to know how you can use these metals. So, for example, mercury is used in thermometers. Silver can be used as an antibacterial. It's just about what use they could have.
Great. And someone has asked if you could please go over alloys again.
Yes, of course. I shall go over alloys. Okay, so remember, alloys are a mixture of two or more elements of which at least one is a metal. So I've drawn an alloy here. This is steel. Steel is made of iron and carbon. So remember, in a normal metal, you have this regular structure of positive ions with electrons, the sea of delocalized electrons around it. In an alloy, because we've got different sized particles, remember these atoms can be different sizes. So carbon is smaller than iron, and we know that from the periodic table because it has a smaller mass. That means that it's going to disrupt those layers. So alloys are often less malleable and ductile because the layers find it difficult to slide over one another because of the disruption of the smaller or larger particles. They have less electrical conductivity, and that is because the delocalized electrons around the cations have resistance when they try and get through the carbon here. So the smaller or larger particles will provide resistance. It's not as easy to flow through that metal as it would be, for example, here, where it's in a nice regular structure, so the electrons can easily flow through it and carry a charge. Are there any more questions?
I haven't seen any new questions come through, but we do have about 5 or so minutes left. So do you want to do a question? Oh, someone just asked if you can do a question about alloys.
About alloys. Oh, there you go. Okay. So oil rigs are used to drill for crude oil. Drills are made from an alloy of iron. The diagrams show the particles in the alloy and in pure iron. Use the diagrams to explain why the alloy is harder than pure iron. So remember, when we were going through alloys, I said that the main thing all the exam boards want you to know about alloys is that they are harder than iron. I've explained some other properties just in case it comes up, and also for your general understanding, but the main one you need to know is why are alloys harder than iron. So does anyone know how we would answer that question then? Why are alloys harder than iron? Yep, so someone says it disrupts the normal metal. The atoms are different sizes, prevent the layers from sliding over each other. That's excellent, really, really well done. So yes, because they've got this irregular structure, those ions cannot slide over one another. So what you can see here is we haven't got these nice neat layers that we have here. So that means that these ions can't slide over one another. So that's exactly why the alloy is harder than pure iron. So it's this disruption of the layers, and therefore the layers cannot slide over one another. We can answer this question. It's about diamond. Drill heads contain diamonds. Give 2 reasons why diamonds are hard. So we would have covered this on Tuesday when we did covalent bonding. Why are diamonds hard? Or which 2 explains why diamonds are hard? Yep, everyone's saying A and D. That's exactly correct. So it has a giant covalent structure, and it has strong bonds between the carbon atoms. You might think that the high melting points would mean that it's also hard. That doesn't. The high melting point relates to when it melts and when it boils, and it's to do with the forces. Something being hard is related to what type of structure it has and the bonds. That's excellent. Okay. Again, kind of another summary question from the whole week. So methane gas is often found where crude oil is found. The diagram shows how atoms bond in methane. Only the outer electrons are shown. Draw a ring around the answer to complete the sentence. Methane is what? Yeah, brilliant. It's a compound. Now, I've been receiving a lot of questions this week asking me what's the difference between a simple molecule and a compound. And this is one of those trick questions where actually methane is a simple molecule. But remember I said that covalent bonding forms simple molecules or giant covalent structures, and simple molecules can be compounds or they can be elements. And the reason for that is it depends what is making up that simple molecule. So remember, something like nitrogen is only made of nitrogen. It's got a triple bond between it, and that's just about the sharing of electrons. If you want to cover that in more detail, go back to Tuesday's lesson. So therefore it would be an element, it's only made of nitrogen, whereas methane has carbon and hydrogen in it, and they're chemically combined, and therefore it's a simple molecule as well as a compound. Draw a ring around the correct answer to complete each sentence. The formula of methane is what? Yep, excellent, it's CH4. Name the type of bond between carbon and hydrogen atoms. What bonding is that? Yep, covalent, excellent. So remember, between non-metals, we have covalent bonding. And then our final question for today, explain why methane is a gas at room temperature. Why do we think methane is a gas at room temperature? Okay, a lot of answers come through. Someone saying it has a low melting point, someone saying weak intermolecular forces. Okay, so you're both on the right lines there. One is slightly wrong. So explain why methane is a gas at 20 degrees. It's because between molecules of methane, there are weak intermolecular forces which require very little energy to overcome, and therefore the boiling point, remember, for something to become a gas, it has to boil, not the melting point. The boiling point is low in methane, right? So just remember, in these questions, often it's really easy to say melting or boiling. Make sure you use the right one, depending on whether something's a solid, a liquid, or a gas. Okay, well done to all the people that answered those questions. Really good. Yeah, it doesn't have strong intermolecular forces, it has weak intermolecular forces. Well done. Intermolecular forces by definition are weak. In slide 12, does picture E have a low boiling point? Thank you for telling me it's slide 12. Let me have a look. Does it have, no, so slide E is graphite. That is graphite. So remember, graphite's one of those odd giant covalent structures where it actually has covalent bonds and it has weak intermolecular forces. So there's covalent bonds between the layers. So sorry, between each, in the layer, sorry, I should say. So these covalent bonds here, it forms 3 covalent bonds with each carbon atom. But then there's these weak intermolecular forces between the layers. But in graphite, it's one of those, as I said, it's a bit of a strange one where actually to melt or boil graphite, you have to break both the intermolecular forces and the covalent bonds. Usually, if intermolecular forces are there, you break the intermolecular forces, but in graphite, you have to break both, and that's just, it just makes it an exception to the rule. So graphite will have a high melting and boiling point. How do you get pencils with different hardness? Again, that's to do with the structure of graphite, so it will depend on how many carbon atoms are within that graphite, how closely packed those layers are, as well as that it may be an alloy, so there could be a metal in there. So some pencils now have got metals in them, and the other thing it's mainly to do with the mass of the graphite, what's in there. Any other questions before we finish?
I don't think there's anything else. So I think it's probably a good place to stop. Thank you everyone for joining us today for the session. Look out for the recording afterwards. And yeah, if you're sticking around, then at 11 o'clock we have an English GCSE session as well. So hope to see you all there. Thanks guys, bye.
Thank you.